Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former Professor and Head of the Department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series intended for the BSc Physics Honours students. We have been going through a course of lectures on optics, and presently we have been seeing a few lectures on wave optics. And by wave optics, what we mean is light is traveling in the form of waves, and light waves are coming from 2 coherent sources. They will interfere and will give rise to what are called interference bands. And the phenomenon of interference, as well as the other phenomena which we will be seeing in the lectures to come, such as diffraction and polarization, can only be explained by wave optics. That means by only assuming waves to light to be made up of waves, and not light is made up of rays as was conceived by Newton. So Newton's corpuscular theory becomes invalid, and we have to invoke the wave theory to explain the phenomenon of interference. And in the last lectures we saw the conditions for constructive interference and destructive interference. Thereby we get a bright band, dark band, bright band, and so on the surface of a screen from the 2 coherent sources. And also one should bear in mind that due to dissimilar reflection there will be a phase change of pi. And again I will emphasize through the diagrams what we understand by constructive interference and similarly destructive interference. And now we will see in today's lecture the so called wedge shaped film. What do you mean by wedge shaped film? You get a air wedge. Supposing you got an object here, and assume this to be a glass plate, and I place a piece of wire or paper, and I got a plate here and another plate here, and in between the 2 plates I am putting a pin, or you can assume this to be a pin or a paper or a wire. Thereby I make an angle of inclination between the 2 glass plates, theta. Because of this, you call this as a wedge shaped film. It is called air wedge because air is entrapped between the 2 surfaces. And this lecture, as well as the next lecture, we will be seeing rings formed when you have a lens on a glass plate. I am putting a wire, 2 plates between which I place a wire. Instead of that, I place a glass plate and a lens. I will be getting a so called Newton's rings, and in both cases the points which I will be emphasizing will be common. And the contents of this lecture are the phase change due to reflection, which I want to emphasize once again, waves in phase and out of phase, air wedge, expression for the fringe width or the bandwidth. The experiment which we will be making use of to measure the diameter of a thin wire or thickness of a paper. So, this is what I mean by the phase change due to reflection. As I told you in the last lecture, when a light ray is incident from air into glass, it may be glass or a bubble, soap bubble of a higher refractive index, n greater than 1. You got n here equal to 1, that is air, you got n equal to 1, that is air. So, light ray when it is incident from air into glass or some other medium of higher refractive index, then there will be a phase change of pi. Okay, there will be a phase change of pi. That is what I mean by a phase change. Ray 1 and this ray 1 is getting reflected, there will be phase difference of pi. That should be taken into account when we want to calculate the the total path difference and or the phase difference equated to n lambda. The total phase difference should be equal to, or path difference should be equal to n lambda. And so this is what we mean by optical path difference. You have got two light rays, light sources S1 and S2, or light rays emanating from source S1 and S2, and of the two distances S1p and S2p, you will know obviously S2p is greater than from S1p by how much? By S2n, right? Drop a perpendicular from S1, draw a perpendicular to S2p, this will meet at the point n. So, S2n is the additional path travelled by one of the light rays, that is a light coming from source S2, you travel through an additional path, that is your path difference, and this path difference is to be calculated in the case of air wedge or Newton's rings. So, we will now once again I will show the condition for constructive interference. What do you mean by in phase? Supposing I sing a song and you also sing a song, and we say the prayer song, Jana, Gana, Mana, and so on. When I say Jana, the other person also should utter the same word Jana without any phase lag. When I say Jana, if the other person say Gana, then there will be a phase difference. There will be, supposing 100 people sing the song, that will lead to, in an incoherent way, that will lead to destructive interference, or there will be only noise, there will be no constructive interference. On the other hand, if I say Jana and all other people, 99 people say Jana, then there will be, the intensity will be 100 times. So, you have no phase difference. If there is a phase difference or a phase lag, then there will be only noise. There will be only some sound heard in an incoherent sound, that is so called the destructive interference. When will you have constructive interference? You have a light source A and other light source B. Light wave is coming from A to C, and another light radiation is coming from B to C. You have got two waves, and if a crust meets a crust, right? If there is a, what is the difference between these two waves? So, you draw a perpendicular from here to the line BC, LBC. LBC and LAC, they differ by what? Tell me, what is the length by which LAC and LBC differ? They differ by one full wave. Is that right? That is the point I want to make. So, if you draw a perpendicular from here to here, it will meet the line BC at this point. So, this will be the one, this is one full wave, right? Path difference is 0 or lambda or 2 lambda. That is a condition for constructive interference. That should be remembered. The path difference should be 0 or lambda or 2 lambda or 3 lambda or n lambda. On the other hand, if the crust and trough meet, how much is the path difference? It may be lambda by 2. From this kind of diagram which I will be showing now, you have in one case the two things are in phase. If the difference between these two, that is LBC and LAC, if the difference is lambda by 2, that will lead to so-called destructive interference. Now, why I am telling these two, or why I am showing these two diagrams, is due to the following reason, namely these two ideas which I have been emphasizing in this lecture also will be finding their places in a case of air wedge as well as in the case of Newton's rings when you are calculating the total path difference. So, when you calculate a path difference, you should take into account the phase difference or path difference due to dissimilar reflection, light coming from that is a rarer medium getting reflected at the interface of a denser medium. Second thing is, as I told you, I showed you the full wave. If the wavelength is one full wave, that will be, or two full waves, that will lead to constructive interference. If lambda by 2 or 3 lambda by 2, that will lead to destructive interference. So, consider a wedge shaped film. What do you mean wedge shaped film? You got a glass plate here, you got another glass plate in this having this kind of orientation, make an angle theta with respect to glass plates. How do you make this theta? By interposing a wire here. You have a wire or a paper, you have between these two glass plates a wire, introduce a wire, then obviously this glass plate will be having some sort of inclination that I call as theta. The thickness of the film increases from O to P. Obviously, the film is, you got air film, right? You got a air gap, you got the film thickness, and so the thickness goes on increasing. You may ask the question, what is the significance of the air wedge experiment? First of all, the fact that you are getting interference pattern, you get a pattern, that interference pattern can be explained only on the basis of wave theory. Apart from that, the practical significance is the thickness of a human hair can be determined by air wedge. It has got forensic application. In the case of murder or something, a hair is something, from person to person, the thickness of hair will be differing, and so the certain mysteries over the deaths or murders have been solved by finding the diameter of the wire. The experiment may appear to be simple. Anyway, this kind of concept of determining the thickness of paper or a thread or a wire or a hair, these things have got a lot of practical significances. Now, therefore, when a ray of light is coming from source, yes, it gets reflected at the phase OQ on the top surface of the glass plate, and the reflected ray travels along the direction B. On the other hand, a part of the light beam undergoes refraction, goes through the medium here, air medium, that is air wedge, travels along this route AC, comes here, meets the glass plate at CD, undergoes refraction at a point D, D the light ray coming out. Now, you have to look at the two rays AB and DE. AB and DE, what is the path difference between AB and DE? We have to calculate the path difference between AB and DE, between these two light rays. One is the light ray traveling in this direction, SAB, right, along this route. The other is traveling through extra length, right, AC and then CD, and comes again along DE. Okay, this is the extra path traveled by one of the light rays compared to the other light ray. So, we have to calculate the path difference. Having calculated the path difference, you know the condition for constructive interference, and that condition should be made use of now. So, again I am showing in an expanded version of the same diagram. So, equidistant alternate dark and bright fringes will be observed. When you have a microscope here, as I will show you shortly, you got a microscope and you can see you plate everything below at the the glass plate, and then you have a wire, another glass plate kept over the wire, and see through the microscope you will be seeing alternate bright and dark bands if the entire pattern is system is illuminated by a sodium vapor lamp. You know the wavelength of sodium vapor lamp. It is a monochromatic source for all practical purposes of wavelength 5893 angstrom unit. the fringes are parallel to each other, unlike the case of Newton's 6, which I will be discussing in the next lecture. The interfering rays are A, B and D, right? A, B and D, as I told you, are the two interfering rays. Let us try to calculate the fringe width or band width. Having told that I will be getting bands, we have to calculate the fringe width. We will have a break at this point. Welcome back at the break. We have been seeing the problem of air wedge. It is called air wedge because you got a wedge shaped film, air film here. As I told you, if this wedge shaped film is illuminated by a monochromatic source such as the sodium vapor lamp, you can see in the field of view alternate bright band, dark band, bright band. You see through the microscope, you can see lines, bright line, dark line, bright line, dark line, so on. Okay. So you can make the crosswire that you see through the microscope, you can make the crosswire to coincide with one of the lines and then make it to coincide with another next successive bright line. The distance that separates two successive bright lines or two successive dark lines or bands is called the bandwidth. So now we have to obtain the expression for the bandwidth, because how will you obtain the expression for the bandwidth? As I told you, you should talk about because you are getting fringes which are alternately bright and dark. That means, like the Young's double slit experiment, it is due to the phenomenon of interference. So you have to look at a condition for constructive interference between the two light rays. That will lead to a bright band, or that condition is not satisfied. If the condition for darkness is satisfied, you will be getting a dark band. So the expression for the fringe width or the bandwidth is the condition for a dark fringe is 2 mu t cos r is equal to m lambda. That is what we have seen in the last lecture. The condition for bright fringe will be 2 mu t cos r equal to m plus 1 into lambda by 2. On the other hand, the condition for dark fringe is 2 mu t cos r equal to m lambda. And here for air, mu is equal to 1, and for normal incidence, cos r will be equal to cos theta, theta will be equal to 0, so cos 0 is 1. Suppose you see the mth dark band or fringe, it is formed where the thickness of the film is Tm. As I show now in this picture, you see what is Tm. You have xm. What is xm? It is a point away from O. You have got O here. The distance that separates O and xm, that is the distance called xm. What is xm? Xm is the place where you got a mth bright band, okay, and or mth dark band. As I told you, the distance that separates the two bright bands or two successive dark bands is the same. So you got now we are concentrating on the dark bands. It doesn't matter whether you concentrate on bright bands or dark bands. Now you are concentrating on the mth dark band. Here the film thickness is Tm. For the m plus 1th, the next band, that because the air gap thickness is increasing, so it is Tm plus 1. Obviously Tm plus 1 will be greater than Tm as is seen in the diagram. And what is this D? D is the diameter of the wire. You got a wire here, I have got a plate here, and okay, you got a plate here, okay, another plate here, and the wire is interposed, right? The wire is interposed, and that is this is the diameter of the pen, or the diameter. This is the diameter of the wire. So D is the diameter of the wire. Let us go back. So you have the formula here, 2 mu t cos r m lambda. Your cos theta or cos r is equal to 1. So the condition that you are getting is 2 mu t, mu is 1 again. For the mth dark band, the thickness will be Tm, okay. In the place of T, I will be putting Tm. And similarly, for the m plus 1th band, I will be putting T suffix m plus 1. They are the thicknesses of the air gaps, right? T is the thickness of the wire, or a small d is the thickness of the wire, or T is the thickness of the wire, and Tm and Tm plus 1 are the thicknesses of air gap which are found corresponding to the mth dark band and m plus 1th dark fringe or the dark band. Therefore, I will be putting 2 into 1 into Tm into 1 into m lambda, that is 2 Tm will be m lambda. Similarly, for the m plus 1th dark band, I will be getting 2 Tm plus 1 is equal to, because it is m plus 1th band. So, I have got m plus 1 into lambda. From these two equations or subtracting, you will be getting obviously this expression m plus 1 minus m will be lambda. Okay. That is your xm plus 1 and xm are the distances which are separating from the point Q. You have the mth dark band here, m plus 1th dark band here, d the diameter of the wire. All these things are known now, and so you can now write down xm plus 1 and xm, they are the distances, right? D the diameter of the wire, L is the distance that separates the point O and the wire. If it is so that is your capital L is here, then your Tm will obviously is a tangent of Tm is what? It is a tan theta, right? Tan theta will be Tm by xm, right? So, I have Tm plus 1 by xm plus 1, because theta is same, Tm by xm, that is d by, that is also equal to d by L, right? That will be equal to theta. Where what is d? D is the place where the wire is kept. So, Tm plus 1 by xm plus 1, that is equal to Tm by xm, because theta is the same, d by L. From here, you are getting Tm plus 1 is equal to, you equate these two, d by L into xm plus 1 will come to the numerator of the right hand side, and similarly combining these two equations, you will be having Tm will be equal to d by L into xm. Now, we have got expressions for the thickness of the m plus 1th dark band. What I mean is the thickness of the air gap corresponding to m plus 1th dark band. This is the m plus 1th dark band, and this is the point where I get the mth dark band. So, your xm minus xm plus 1, this the difference between xm plus 1 and xm will obviously give you the bandwidth or the fringe width. That is what you have to obtain now. So, that is an expanded diagram which clearly shows your xm and xm plus 1 and so on. So, the distance that separates xm plus 1 minus xm, that is your bandwidth. Okay. Now, from the expression that you got here, you can subtract these two things, and your xm minus xm, you can take your L and other things to the other side, and so 2d by L into xm plus 1 minus x suffix m is equal to lambda, and this, as I told you, the bandwidth, right? That is the bandwidth. So, 2d by L into beta will be equal to lambda. So, beta will be, so the important expression will be, what is the expression for bandwidth? Beta will be lambda, that is wavelength of the sodium vapor lamp, multiplied by L divided by 2d. What is L? L is the distance that separates the end point of the two glass plates and the place where you got the wire. Okay. L is known, you can measure, it will be of what magnitude? It will be 5.7 centimeter. It will be in centimeters. L can be measured. L is a measurable quantity. Beta is the one that is being measured in the laboratory. How do you measure beta? Make the crosswire to coincide with the mth bright band, then move the crosswire to coincide with the m plus 1th bright band, or mth dark band, and m plus 1th dark band. As I told you, it is immaterial whether you concentrate on the bright band or the dark band. Therefore, beta is a thing that can be measured. If beta is measured, because L, as I told you, is known, you have to assume lambda. It is 5893 angstrom, and so your d, what is d? The diameter of the wire can be determined. This is a side view. This is what I have been telling you all along. You have got a glass plate here. If we have the paper or the wire, in this case you have got a wire interposed between the two glass plates, that gives rise to the bright and dark bands, and the distance between the two bright bands is beta. Similarly, distance between two dark bands will be again equal to beta. The bands are shown from the point of view of understanding. To get a better understanding, they are shown so thick, but they will be very sharp. So you can take this band, center of the band, center of the band. The distance separating two bright bands is beta. Distance separating two dark bands is again beta. Beta is a thing that can be measured by making the crosswire to coincide with the mth band and m plus 1th bright or dark bands. So you have to consider two successive bright or dark bands. Having measured beta, it is easy to determine the diameter of the wire. The interference fringes in an air wedge are regularly spaced as shown in the diagram. That is what you are getting now. So an air wedge is formed by inserting the wire between two glass plates. That is what I told you earlier. Monochromatic light is reflected vertically downwards on the air wedge by the inclined glass plate G. A travelling microscope M is used to see the fringes. This is the diagram. You have got a coherent source. For the ephemeral point of view, this is the coherent source, that is a sodium vapor lamp. You have got a lens here. The light is passing in this direction. The inclined, you have got an inclined glass plate. That plate reflects the light beam to go through the air gap. You have got an air gap here. You have got a sheet of paper which has been magnified many times. The sheet of paper or a wire that is kept here, that makes an angle theta or alpha as shown in the diagram, and you have got the mth dark band here, m plus 1th dark band here. By making the crosswire, you see the travelling microscope and make the crosswire to coincide with the mth dark band. Next, move the crosswire, move your microscope so that the crosswire coincides with the m plus 1th dark band. The distance that separates the two bands is beta. So the beta is measured. The microscope is focused to get a clear dark and bright bands. The fringe width beta is measured. The length L of the wedge is also measured. Knowing lambda, the diameter D of the wire is calculated using the formula here. This is the formula that should be used now. So apart from determining the thickness of the wire or paper, this experiment can also be used to test the optical flatness or whether the surface being tested, any surface that you see, it looks to be plane. Plane means what? It is plane means for the common eye it looks to be plane, but exactly speaking it may not be optically plane. The surface looks like this, but it may be wavy. So a wedge shaped air film is formed between an optically plane glass plate OP and the surface under test OQ. If the surface under test, where is your OQ? OQ is this surface, right? OQ is the surface. If the surface is not plane, the bands will not be exactly uniformly spaced. The bands will be wavy bands. The bands will be irregular. Let me now pass on to the summary of the lecture. A wedge-shaped film is formed when one glass plate is kept inclined with respect to another one by having a thin wire between the two glass plates. Bright and dark fringes are obtained depending upon the thickness of the film. Expression for the width of the fringe is obtained. Air wedge experiment allows one to determine the thickness of thin materials like paper or a wire or hair and so on. The questions which are to be asked for the lecture are the following. What is air wedge? Question number 2. Mention the conditions for obtaining bright and dark fringes. And the last question, give the expression for fringe width. With this we come to the end of the lecture number 18, The rest of the things we'll see in the next lecture. Thank you.